Well, howdy. So let's sort of keep ziplining. Um, so last time we talked about just calculating the work in this situation where we had the two trees over a river with a crocodile in it, and you had a platform here and a platform here. This will make the trees a little bit taller. You were ziplining down from one platform to another, and this distance between platforms was 120 feet. And what I didn't mention last time is that when you started your zip line down, you dropped your wallet. Now, fortunately for you, your wallet did not drop onto the head of the crocodile. Instead, there's another platform parallel to the platform on this other side, just below where you were, and it fell onto that platform. So that was lucky. That was very lucky for you. But we want to figure out here, and what we're going to do is we're going to figure out what the speed the wallet hit on this platform is compared to the speed that you hit on the opposing platform over there was. So we're going to look at those two speeds and see how they relate to each other. And we're going to do that with the work energy theorem, which says that the work is equal to the change in the kinetic energy. Both you and your wallet right up here have zero kinetic energy because you haven't started moving yet. When you get down here, you'll be at your maximum speed of the problem. So that's how we're going to figure this out. So that's the main idea of this problem. That's what we're going to look at. Remember, what we decided was the easier way to do this was to use the work is equal to the force times the distance parallel to that force. And the force is just your weight, and you weigh, in this case, 150 pounds, right? That's what we did last time. 150 pounds of force. 150 pounds of mass is the mass that gives you 150 pounds of force on the surface of the Earth, or thereabouts. And then the distance is 120 feet. And that's an awful 2. And that multiplication we said was 18,000 foot-pounds. So then what we want to do is we want to figure out how to use this equation here to get the final speed, the speed when you're here, right? And we'll do the same thing over here to see which one's faster. Do you have any idea right now which do you think is going to be faster when it gets there? Remember, this is going straight down. You're going at this angle. It's going to take you a lot longer to get down there, right? This is going to go straight down. It's going to get there really quickly. You're going to take a greater amount of time to get here. So the question, but that's not the question. It's not the amount of time that we care about, right? It's the amount of speed that you have when you get there. So you can think a little bit about that. We'll, at this point, just try to figure out the speed using the work kinetic energy theorem, which is basically going to say that this work that we just calculated, this guy is that guy, is equal to the initial minus the final, or final minus initial kinetic energies, which is 1/2 mv squared. So that's 18,000 foot-pounds is equal to 1/2 times your weight, which is 150 pounds of force, times v squared. Okay, so that means we do a little bit of math. So that's 75, right? This guy here is 75 pounds of force. This is 18,000 feet per pound. Let's see, that means, can't get 75 into that, you have to get 75 into 180, that's 2. That's 150, so then we have 300, that's 4, and at that point there's nothing left over, so that's going to give us v squared is equal to 240. Let's let's see, feet per second squared. And then, we, oops, got this squared. And then we just take the square root. Right, and that is going to be, do you know the square root of 240 offhand? I don't. Well, maybe it's 15.5, let's say, feet per second. Or feet per second. Okay, so we're going to say that you're going at 15.5 feet per second when you get down to that platform down there. Sounds fast to me, but you can take it. You're tough. All right, so let's see if I'm right. Okay, I am right. It's 15.5 feet per second. Good. So at least I agree with what I did earlier to make this slide. So now let's do the same thing for your wallet, right? W equals FD parallel. In this case, the force is 1 pound of force times 120 feet, which is exactly 120 foot-pounds. Right? This is exactly how hard the world is. And that's the amount of work that's done to that wallet. All right, so that's the amount of work done to the wallet. So you might be at this point thinking that's a lot less work done to that wallet than to the Zipline or to you. So what does that mean about the speed? Well, we do 1/2 mv squared. We have 120 on this side pounds of force is equal to 1/2 times 1 pound of force or pound of mass times v squared. All right. And that means that v squared is equal to twice 120 divided by 1, which is 240 feet per second squared. Is that right? Or feet squared per second squared, excuse me. But is that right? Seems like that ends up being exactly the same speed. Even though, as we said, the wire here, this wire, is making you go on a larger distance, and it's reducing, if you remember from the last episode, or it's not an episode, from the last episode, I can't remember what this is. Example, okay. So you remember from that the tension is pushing this way, so that the force in this direction is less. So the force in this direction is less, but it's longer, and it happens to exactly compensate for that as far as these final speeds are concerned. So that's a second interesting thing. So the last time we just talked about how using this or the other formula that I gave you is something you should think about in terms of what sort of things do I know, which way is it easiest to get the number. Although the other formula was a little bit more real. It was more like this one, right? In this case, the distance that the wallet traveled is exactly parallel to the force. So there is no parallel that we have to worry about. Each one is parallel to the other already. In this case, all we learned is that it doesn't matter your weight. It matters, that parallel distance and the force. That's all that matters, right? We're not worried about your weight. We're not worried about we're not worried about the angle or anything like that. All we care about is these two things. And when it comes out, when we use this work kinetic energy theorem, your mass doesn't really matter. How much you weigh doesn't matter so much as what actually happened. Because it's gravity, that's actually a special property of gravity. All right. So that is it. That is all for problem 2 or example 2. I will see you soon. Bye now.